Hi all, my name is Sydney Nader, and today I'm going to walk through the design and fabrication through a breadboard of a Class D amplifier. So this amplifier has 5 core subcircuits, the first being a triangle wave generator, the second being the preamplifier, third being the comparator, 4 being the gate driver and MOSFETs, and the 5th subcircuit is the LC filter that outputs to an 8 ohm 1 watt speaker. So I'm going to walk through how I designed this. I'm going to walk through each subcircuit, schematic and specifics. I'm going to walk through key measurements taken throughout each subcircuit to ensure that when I move on to the next one, we're working with very good signals. And then I'm going to show the output functionality of the speaker. So let's dive in. All right, so this is the first subcircuit, the triangle wave generator, and this consists of a monolithic timing circuit that produces a square wave and an integrator circuit that uses an operational amplifier to convert that square wave into a triangle wave. So this subcircuit serves as the reference signal in the pulse width modulation, or PWM, process, where it's compared to the audio signal at the comparator to generate a PWM waveform. So let's focus on the square wave generation first. So for the square wave generation, a TLC 555 timer configured in astable mode was utilized to produce a high frequency square wave. And this component was chosen because it is a CMOS implementation of the 555 timer, meaning that it's capable of much faster switching speeds and has lower power consumption compared to traditional bipolar versions of this timer. These characteristics make it a well-suited choice for high-frequency applications such as this Class D audio amplifier, where stable, clean waveform generation is critical and desired. So the oscillation frequency of this square wave is set by a 1K resistor, a 5.1K resistor, and 2 parallel capacitors of 100 and 220 picofarads, resulting in a total capacitance of 320 picofarads. And these component values were selected using the standard frequency equation with the goal of achieving a very high frequency above 300 to 250 kilohertz to ensure that the reference signal, which is the triangle wave in general, will remain at a greater frequency than the audio signal frequency. And this we will dive into later, but the purpose is for proper comparison at the comparator. One thing important to note is that the TLC 555 is powered between a positive and negative 5 volt supply, resulting in an output square wave that swings between approximately 5 and negative 5 volts, producing a 10 volt peak to peak signal. And this voltage swing will ensure that the integrator generates a triangle wave with sufficient amplitude for comparison with the amplified audio during the PWM process at the comparator. So let's take a look at this resulting square wave. So we can see that the output square wave has a measured frequency of approximately 330 kilohertz, a duty cycle of about 54.4%, and a peak-to-peak voltage of 10 volts with minimal to no DC offset, making it suitable for generating a stable and symmetric triangle wave through integration. Alright, so now that we have a suitable square wave, let's move into the second part of subcircuit 1, which involves the integrator. So the integrator is going to convert the square wave into a triangle wave by summing the input signal over time, causing the voltage to ramp up and down with the square wave's transitions and at the same frequency as the square wave. This integrator circuit utilizes the OP37 op-amp, chosen for its high bandwidth, low input offset voltage, and fast slew rate. When deciding which components to utilize for the integrator circuit, the equation RC equals Vin times period divided by 4 times the peak voltage desired was utilized, which is the equation for a simple op-amp integrator. The integrator calculations resulted in a resistor value of 5.2 kiloohms and a capacitor value of 470 picofarads. However, during initial testing, it was revealed that the 5.2 kiloohm resistor introduced noise and instability into the triangle wave output. So to address this, I replaced that resistor with a potentiometer, and this allowed me to do some fine adjustment and resistance. And the tuning determined that a 2.4 kiloohm resistor produced a significantly clearer and more stable triangle wave. So let's identify the other components that are a part of this integrator. So a 10K resistor was placed in parallel with the feedback capacitor to establish a DC feedback path, helping prevent output drift and maintain stability. Due to small imbalances in the input signal and component tolerances, I noticed a small DC offset was remaining at the output. Therefore, I added a small positive bias voltage to the non-inverting input of the OP37. And to do this, I used a power supply to see exactly what voltage would be sufficient here, and then from that power supply voltage value of 0.19 that I came across, I created a voltage divider circuit to accomplish that, pulling from the positive 5 supply. So for the last note about component selection in this circuit, let's talk about the RC filter at the output. We can see the 3.3 kilo ohm resistor was placed at the output, forming part of the voltage divider that biases the non-inverting input of the OP37. So this resistor also works in combination with the 10 picofarad capacitor at the integrator output to form a first-order RC low-pass filter. And this filter is there to help suppress high-frequency noise and improve waveform stability without significantly impacting the triangle wave. And just to be sure that this would not negatively impact the triangle wave, I performed a cutoff frequency calculation to be sure that the cutoff frequency of the RC filter is much larger than the desired signal of interest frequency, which is that 330 kilohertz. So the cutoff frequency for the RC filter came out to be 4.82 megahertz, which is well above the 330 kilohertz signal of interest. All right, so now that we've taken a look at subcircuit 1's schematic, let's dive deeper into the output signal. The final triangle wave with a frequency of 330 kilohertz and a peak-to-peak voltage of about 5.6 volts can be seen here. The slight asymmetry in the wave is caused by the input square wave's imperfect duty cycle of 54.4%, resulting in uneven rising and falling slopes. But this distortion is very minor and it will not significantly affect performance since this waveform is only being used as a reference in the comparator for PWM generation. So now let's take a look at subcircuit 2, which is the preamplifier. So this preamplifier uses a non-inverting amplifier configuration powered by a positive and negative 5-volt supply to receive the left and right audio signals and amplify them for improved signal strength and enhanced SNR at the comparator. So to ensure that the left and right audio outputs from the iPhone's audio jack are both included, 1 kilo ohm resistors were placed in series with each channel before summing them together at the input of the OP37. To achieve sufficient amplification for signal comparison, a voltage gain of 4 was selected. So the audio signal that comes off of the iPhone 5S initially has an approximate peak-to-peak voltage of 1 volt, which is too small to be effectively compared against the 5.6 volt peak-to-peak triangle wave that was generated in subcircuit 1. So amplifying the input signal by a factor of 4 increases it to approximately 4 volts peak to peak, which is sufficient for comparing the audio wave to the triangle wave generated earlier. The standard gain equation was utilized, setting gain equal to 1 plus R2 over R1, and that is how both resistors were selected for this amplifier. Alright, so now that we've walked through the component selection for the preamplifier and the schematic, let's take a look at the output signal. So we can see the original signal is in orange and the amplified output signal is in blue. The output reaches approximately 4 volts peak to peak and is centered around 0 volts, confirming that the preamplifier is functioning as intended with a gain of 4 from the original audio signal. So now that we've walked through subcircuits 1 and 2, we're ready to move on to subcircuit 3, the comparator. So this subcircuit utilizes a high-speed comparator using the AD8561 to compare the reference triangle waveform generated by subcircuit 1 with the amplified audio signal that we just discussed with subcircuit 2. And in the schematic here, we can see that the reference, or the triangle wave, is coming in at the non-inverting terminal, whereas the signal, or the amplified audio, is coming in at the inverting terminal. The AD8561 comparator operates on a dual power supply. However, the output oscillates between 0 and 5. It is important to note that unlike comparators with open collector outputs, the AD8561 was selected for this project because it has a push-pull output stage, which simplifies the connection to the TC4420 gate driver by removing the need for an external pull-up resistor. So now let's take a peek at the comparator PWM output signal. Here we can see the comparator PWM output signal, which looks like a square wave, and it correlates with a digital signal where the duty cycle corresponds to on and off time that will be translated to the gate driver in the next circuit. One thing important to note is that the comparator stage was designed with specific voltage and frequency constraints in mind to ensure optimal operation of the AD8561. So especially important was the frequency of the triangle reference waveform, as it needed to be significantly higher than the maximum frequency content of the audio signal for reliable PWM generation to occur. Now that we have a successful PWM output signal from the comparator, after taking in the reference signal or the triangle wave and the amplified audio wave, we can move forward to subcircuit 4, which is the gate driver and MOSFETs. So taking a look at subcircuit 4 with the gate driver and 2 MOSFETs, the gate driver provides the necessary current to quickly charge and discharge the MOSFET gates, enabling fast switching and reducing power loss during transitions. The input PWM signal from the comparator is passed to the TC4420 gate driver, which buffers the signal and delivers higher current drive than the comparator could directly supply. The TC4420 works well for this application and was selected specifically because of its strong sourcing and syncing capability, rail-to-rail output swing, and fast switching times, all of which are important for driving capacitive MOSFET gates efficiently at the high frequencies that we're pushing. Now let's take a look at those MOSFETs seen on the right of the schematic. In this subcircuit, the ZVP2210 P-channel MOSFET connects to a positive 5-volt power supply, and the ZVN3310 N-channel MOSFET connects to ground, forming a complementary push-pull output stage. The PWM signal from the comparator is fed to the TC4420 gate driver, which sends the same signal to both MOSFETs through separate output pins. The ZVP2210 and the ZVN3310 were selected for their low gate threshold voltages, fast switching speeds, and compatibility with 5-volt gate drive signals, ensuring that both devices will fully turn on and off with the voltage levels coming from the gate driver. We're going to dive deeper into the NMOS and PMOS switching based on the gate driver input after we look at the LC filter output. But for now, let's take a look at the gate driver and MOSFET's output signal. Here we can see the output signal from subcircuit 4. One thing important to note is that the measured PWM signal is rapidly switching and represents a high-frequency square waveform. The oscilloscope measurement provides a general idea of the output signal at a single moment, but it does not fully capture the dynamic switching behavior of this subcircuit. Observing the audio signal after the LC filter will provide a direct evaluation of the amplifier's ability to reproduce the original content. So let's take a look at that now. We're at subcircuit 5, the final subcircuit, which is the LC filter and speaker output. So the LC filter's purpose is to remove high-frequency noise from the PWM signal, ensuring that only that smooth analog audio signal passes through the speaker. The inductor value of 10 microhenry and capacitor value of 5.7 microfarad were calculated primarily based on setting a cutoff frequency around 20 kilohertz, which matches the upper limit of the audio frequency range. This cutoff ensures that the audio signal is preserved while the high-frequency switching components are effectively filtered out. So we can see the final schematic here, and we're going to dive into looking at some demonstrations. Here's our final breadboarded circuit. We can see here is our power supply. Here we've got an iPhone 5S that will be the audio input coming from this barrel jack. We have the preamplifier here, the square wave generator here, the integrator that creates the triangle wave here. Both of those signals, the preamplifier and the triangle wave, go into the comparator here. The comparator's PWM output goes to the gate driver, and the NMOS and PMOS are here. And then the LC filter outputting to the speaker is here. And if we play, we can hear audio coming from the speaker. I can put the camera a little closer to it. All right, and let's look at this on the oscilloscope now. So let's take a quick pause here so that we can compare the original audio coming in and the output audio signal that the speaker is receiving. All right, so as seen in the waveforms here, the output, which is the blue, closely follows the input audio coming from the iPhone 5S, indicating that the amplifier successfully modulates and reconstructs the audio signal through the PWM and filtering stages. Minor differences in amplitude and slight delays between the input and output are expected due to filtering effects, component tolerances, and MOSFET switching dynamics. Overall, the output waveform demonstrates that the system is highly capable of reproducing the original audio content with high quality, while efficiently removing high-frequency noise introduced by the PWM switching process. All right, so that's all I have for today. Thank you for following me through the design and creation of the Class D amplifier, and I hope you enjoyed.